Okay, good evening. Today we're going to continue talking about what we started last time, the analog to digital conversion. In the last lecture, you see my slides, right?
Yes, Doctor.
Okay. In the last lecture, we started with A to D, what the concept of A to D, how do we convert physical values to electric signals, how through transducers, then the voltage, if needed, should be signal conditioned to convert the voltage into a range and scale that the A to D understands. Then the A to D will convert the voltage, represent the voltage in a digital number, either in 8-bit as an 8-bit number or 10-bit number. This is for the case of HCS12. Okay. We looked at different methods to convert to a digital number, mainly the successive approximation. We spent a little time here, and this is the way that how HCS12 works. And we talked that A to D converters are ratiometric, which means that the digital value is relative to the voltage reference low and voltage reference high that you preset. We looked at some scaling circuits, amplifiers, shift and amplify circuits to do the signal conditioning. And we started talking about the HCS12, and we talked that our HCS12 microcontroller that we're using here, the DG256, has two A to Ds that each with 8 channels that you can configure either in the 8-bit mode or the 10-bit mode. 8-bit or 10-bit. And we said that the clock frequency that runs the logic of the A to D can go up to 2 megahertz. Okay. And we're going to talk about timing more here. 10-bit resolution is always better than 8-bit resolution in terms of accuracy, but it takes more time to read. So if you want to sample faster, then maybe a bit faster, lower resolution would be faster. And when would you want to care about how fast you are? Well, to recover the signal that you're reading, Nyquist law, when you want to sample a signal, right, take samples, the sampling should be more than 2 times, right, the frequency of the signal that you're sampling. And we had a look at this block diagram that shows one A to D, and we have another one, so we have 2 A to Ds. An analog to digital converter that has 8 channels means it has 8 pins connected to a multiplexer that selects only one input at a certain point of time. However, this multiplexer, you can switch it between inputs very fast. Then the signal you take will be sampled, will go through a sample and hold stage. While held in a capacitor, the sample, you take a sample, you charge a capacitor, you hold it for a while this successive approximation logic converts it into a digital number that it is stored in a 16-bit register. Well, sometimes you'll use the lower 8-bit of the 16-bit register. Well, let's say 8-bit, maybe lower, maybe higher, depending on right or left justification. We'll talk about that more. Or you may use 10-bit of the 16-bit registers. And you can configure these pins, the default that they are analog, but you can still configure them to work in the digital mode and treat them as an input digital port, just like port B in its input mode. And we were here last time. So let me try to finish this real quick and start with you a real hardware example. So we said we have 2 A to Ds. The first A to D, we call it AD0. The second is AD1. Each one has 8 channels. So AD0 has channel AN0, AN1, AN2 up to AN7. These are 8 channels. Okay. The other A to D, AD1, also has 8 channels. We start counting after 7. So AN8 up to AN15. So we have 16 channels that we can connect to 16 transducers, 16 sensors, whatever. At a single point of time, you can be reading one channel from here and one channel from here, but because of the fact that you can switch real fast, and most likely you wouldn't need to read the temperature more than once or twice a second, you don't need to read it every 10 microseconds. So that's why that gives you more time to switch between channels. And we really want to save hardware because having 8 hardware analog digital converters, each for one of the channels, that would be so and too expensive. طيب. The analog to digital converters, we can read an analog to digital converter, read the voltage on a pin connected to an analog to digital converter based on our program through software by writing it into a register, or we can configure a pin. When a rising or falling edge, an edge is applied to this pin, it will trigger the analog digital converter module to start reading or converting. So the pin is AN7 in case of AD0, and the pin is AN15 in case of AD1. Voltage reference high and voltage reference low, we can specify them. Usually, they can be the voltage source and ground of the microcontroller. طيب, let's start with the registers that configure our A to D. So in theory, now we know what is an A to D, how it works, how it uses a successive approximation to convert voltage, represent voltage in 8 or 10 bits. The A to D we have on the HCS12 microcontroller has different registers. We have control registers, 6 control registers. The first 2, control register 0 and control register 1, we don't use them. They're reserved for factory testing. So we start at A to D. We said we have A to D 0 and A to D 1. So this X could be a 0 or 1. Meshi? 0 means that you're talking about, you're controlling AN 0 to 7. If this is 1, then you're talking about AN 5, 8 to 15. Meshi? So let's talk about the first 7. A to D 0, control register 0 is not used. 1 is not used. We start with 2. So we have A to D 0 control. This is for 0. If we're using the other A to D, we replace the 0 with a 1. Control register 2. Then A to D 0 control register 3. Then A to D 0 control register 4. And A to D 0 control register 5. We're going to look at each one of those. So we have 4 control registers that we use. We have 2 status registers, A to D 0 stat 0, A to D 0 stat 1. 2 testing registers, test 0, test 1. Then we have these registers that we use when we want to configure the analog digital converter in the digital mode. Okay. Then after you convert an analog value connected to a pin into a digital number, you need a result register, a data register to hold the result, the 8-bit or the 10-bit. So each A to D has 8 registers, 16-bit 8 registers. Why 16-bit? Because there is a probability that you would need to do 10-bit conversion. Okay, so you need more than 8. So we have A to D 0 data register 0, and this up to what? 7. ماشي. If we want to talk about 8 and up to 15, we replace this 1. We make this a 1, then 0 up to 7. طيب. Each of these, this is a 16-bit register. You can deal with it as A to D 0, data register 0, low or high. ماشي. To access the lower 8-bit or the higher 8-bit, because this is 16-bit. In this case, this would be 8-bit, and this would be 8-bit. تمام. Let's start looking at the registers. يعني, we all know our exams, we work, it's not about remembering, it's about understanding. Okay, let's look at these. You'll have them with you when you're going to go program something. طيب, the first thing in the control register 2, we said we don't, control register 1 and 2, 0 and 1 are not used, they're for factory. So we start at 2. 2, the most significant bit in this register is to power up the A to D. The A to D has a power source. So you shouldn't leave it powered up all the time, because it consumes power, right? And if you're battery powered, you want to save power. So usually it's down. If you want to start sampling, start reading an analog voltage, you power it up by making this bit a 1. So when we write our code, this bit should be set to 1. So remember these. So A to D 0, we want to make this a 1. Then there's this bit, which is the fast flag clear all bit. If it's 0, when you're done converging, guys, we saw that successive approximation, it goes through multiple steps, right? It goes to the most significant bit in the successive approximation register. It makes it a 1, converts the digital value into an analog voltage, compares with the incoming voltage. If it's greater, right, it keeps the 1. Otherwise, it brings it back to 0. The other way around, then goes to the other bit, and so on. This thing takes time, in addition to the time for sample and hold. So it's not like in 0 seconds you say read the A to D and you got your result. It takes time. So how do you know that you are done reading the analog voltage? A flag will raise for you, or an interrupt will happen. This flag needs to be cleared when you're done. Okay. Also, so this is about the convergent done flag. Also, there is something called the CCF flag that is assigned to the channel that we're going to read multiple channels sometimes. Okay, when a channel reading is ready, a flag will be raised as well. When you go read the data from that data register that contains the data, the digital code of the analog representing that voltage, you read the data and then you clear the flag. Okay, so to indicate that I'm done, and you can write over it again if you need, and you don't read it again. So there are 2 modes to clear the flag. The first mode, if this bit is 0, you will have to go read the status register, one of the status, then you read the result register. 2 steps to clear it. You manually have to do this. Read this, then this. Or you just set this to the automatic mode, and whenever you read the result registers I'm talking here about these. When you just read the data from the result register, the flag will clear automatically. So usually we set this to 1, automatic clearing. The rest of the bits, what will happen to the A to D in the wait mode? Well, you can decide to keep it working or disable it. What will happen? Well, if I choose to make the A to D to work, to be triggered by AN7 or AN15, what is the trigger going to be, level or edge? طيب, the polarity, if the trigger is going to happen. disable or enable the external trigger if I want it to be there or not. طيب, when I'm done, do I want to enable an interrupt to take me to an interrupt service routine and over there deal with the data I got collected in the result register? If so, then you need an interrupt enable and disable, and an interrupt flag that you clear inside your interrupt service routine, similar to what we did in other interrupts. Today, we'll do an example where we're not going to use interrupt for analog to digital. I just ask it to read and wait for the result to be done. So when we do A to D0, so A to D0 control register 2, it's going to be 1, 1, 0, 0, 0, 0, 0, 0. So this will be what? 0x C0. تمام? Okay. طيب. Then we said if we want to choose external trigger, what's the trigger going to be? On a falling edge, on a rising edge, on a low level, on a high level? We said this. طيب. We're not going to use a trigger. We're going to do it by software. طيب, A to D control register 3. This register says the convergence sequence length, how many times you want to read. Enable or disable the Fifo mode. I'm going to talk about that for the result register. And control what will happen in the freeze mode. In Fifo mode, we'll talk about Fifo mode. In Fifo mode, FIFO يعني first in, first out. Okay, first in, first out. In this case, if you're reading A to D0, the result will be register. If you're reading A to D0, the result will be stored in register 0. If you're reading A to D1, channel 1, the result will be stored in channel in result register 1, and so on. طيب, and every time you go back from 0. This is in the non-FIFO mode. In the FIFO mode, you can choose to start storing at 4, start doing reading things. So AN0 will store at 4, 1 will store at 5, 2 will store at 6, 3 will store at 7, 4 will go back to 0, 2 will do wrapping. Meshi. I'll give more example on that. So this is, but as an idea, what would FIFO be? Convergence sequence length. Now, usually, guys, when you want to read a voltage from a sensor, especially in harsh environments, noisy environments, sometimes that's how people do it. You read, مثلا, if I'm sampling a voltage, ماشي, and we're going to see it today on the scope. I'll show it to you, a scope. You're reading a voltage. Sometimes you can get a spike, which is probably noise. So sometimes you can do this manually. You read the A to D maybe 10 times. Then you average them. Averaging them is like you're reducing the importance or the contribution of this spike, which is something like doing a low pass filter, right? Actually, an averaging is a low pass filter, right? Now, our HCS12, instead of going and reading the A to D multiple times, you can decide from the beginning that I want to take this reading 8 times. Do 8 convergence, read it 8 times. And it will store 8 results in 8 data registers, in 8 result registers, and you can go collect them, average them, and use the average to get better accuracy in case of noise or something. So this is a case. This is a case if you want to do a low pass filter, you can choose to read multiple times. This is one case. Another case, this is where is the other? There's a bit here. I'll show it to you and come back. Enable multi-channel conversion. So we are able to enable conversion across a single channel or across several channels. Yani, if I do 8 conversions or 7 conversions in the non-multi-mode, okay, non-multi-mode, it will read 8 times from this. If I was reading A and 0, it will read this 8 times. But if I enable the multi-mode, it would, and I tell it I want to do 5 conversions, it would read A and 0, A and 1, 2, 3, 4, 5. Okay, across multiple channels. And this would be handy and helpful if you want to read from 8 sensors, maybe in a single shot. Okay. So these are possible uses why you want to do several conversions. طيب. Enable the Fifo mode or disable the Fifo mode. If this is 0, every result will be placed or stored in the corresponding result register. Yani A to D, channel 0 will be stored in the register 0. Channel 1 will be stored in register 1, and so on. But if we choose the Fifo mode, the conversion result will be stored in a result register that I specify somewhere in later on. And when I get to the last one, which is register 7, wraparound will happen. You go back to register 0. We'll see some examples. Then what we want to do in case the freeze mode. We're not going to look at this.
دكتور هسه لما يكون واحد بصير بالعكس ليفو بصير صح؟ بصير لاست
لما يكون واحد you enabled FIFO.
لما يكون مش احنا قلنا لما يكون واحد
No, it doesn't mean LIFO. FIFO, the opposite of FIFO, it doesn't mean LIFO.
شو first input first output هذيك last input
yeah, it's a name. لا هذيك non-FIFO. They call it non-FIFO. Non-FIFO means A and 0 stored in A to D0. A and 1 stored in A to D1. When you get to 7, you're stored at 7. Period. You go back, read 0, you store at 0. And that's it. But in the FIFO mode, Yazid, you can choose to start reading from A and 4, مثلا. 3 times. So you store the first result and you specify when you want to store, مثلا at 0. So 4 will be stored at 0 here. The next reading will be stored here. The third reading will be stored here. Okay. If you read again the next time, you will not go back to 0. You won't reset. You will continue. You continue. You still the first reading will be at 3, second at 4, third at 5. Next time you read, you continue. 6, 7, you go back to 0. Okay. So it's a FIFO and non-FIFO. طيب. So when we set this register A to D0 control register 3, let's do one conversion in our case. Meshi. Let's do one conversion to ease in it. So one conversion is, this is 0 by default, 0, 0, 0, 1. And I don't want the FIFO mode, and disable continue conversion in the background, and you don't worry about the freeze mode. So this would be 8 and this would be 0, right? So 0x 08. When we write code, this will be handy. This is control register 3. Control register 4. This mainly sets the resolution and conversion speed. We said that our A to D can work in the 8-bit resolution mode or 10-bit resolution. So this bit, you either set it to 0, by default it's 0, it is 10-bit conversion, yani the voltage will be converted into a number that ranges from 0 to 1023, right? This is the 10-bit conversion mode. You can choose the 8-bit operation mode, then your reading will be a number from 0 to 255. Tamam. And again, for easiness, and 0 to 255 is something not bad yet. So let's do 8-bit conversion. Then we come to these 2 bits, SMP1 and SMP2, and these select the sample time bits, okay, for the second phase of the sample and hold cycle. How many clock cycles we're going to do. Guys, this process, when you sample here, you sample, you close this switch, start charging this capacitor. This is 2 stages. Yani, there is a must to have 2 clock periods here, plus something of your choice, 2 or 4 or more time will enable the capacitor to charge more, getting to higher levels of accuracy, yani reading a more accurate voltage. Okay, but it will take more time. So it's a compromise. It is something optimization problem. More you get more accuracy, but much more time, because when you charge a capacitor, we said last time, to reach its 100% through an RC circuit, you may reach the 90% over here, but to get to the final value, you'll need maybe double the time. Maybe so 90% is probably, if it's for your application is okay, you can do that. So how long we're gonna do the sample stage, the second phase. So the 2 cycles are mandatory. We can add up to more, 2 or 4 or whatever. So these 2 bits decide how many cycles we're going to add in, to the second phase of the sample phase. So these 2 bits, if you keep them at 0, then you're adding 2 converging clock periods. Yani 2 من أول, 2 from the first stage, and 2 from the second. The total is 4. You can add 4, you can 8 or 16. Okay. So in our case, let's add 2. So these will be zeros. طيب, what is the clock period? We said that the A to D clock period is something between half a meg to 2 megahertz. Right? 2 megahertz. How do we configure the clock speed? How do we configure the clock speed? It depends primarily on the bus clock. So it's a factor of the bus clock. The bus clock, so it matters if we're using PLL or not. Times a half over a prescaler plus a 1. If we want to set this A to D clock to the max, yani 2 megahertz, and we did use PLL, like last time, yani 48 megahertz. So the bus clock in this case will be half of it, yani 24 megahertz. So 24 megahertz over something prescaler plus 1 times 0.5. What would be prescaler to make this a half? So 24 times 0.5, this is 12. 12 divided by how much to get the 2? By 6. So 1 plus this would be what? 5. So, following with me, guys? So these bits, to get the 2 megahertz, and if my PLL is at 48 megahertz, if PLL is 48 megahertz, then the bus is 24 divided by this. Okay, so you can compute it by this formula. And for people who are not good in math, you can use this table. Yani in our case, this is what we did, right? Our maximum bus speed at 2 megahertz, and our bus speed is 24. Okay, so our prescaler will be what? 5. This is what we just computed. Meshi? So this would be these PRS bits from 0 to 4 هذول would be 5. يعني 0 لا 5 would be, sorry, erase this one. Pen. 5 will be 1 0 1 0 0 صح? So A to D 0 control register 4 would be what? 1 0 0 0. These are what? 8
8 5.
8 5 85. طيب. So this register 4 is 85. Register 3 is 8. Register 2 is C0. ماشي. The last one is control register 5. A to D0. Register 5. Here we set the justification, how the data is justified. Left justified or right justified? What does this mean? What does this mean? We said that result register A to D, is it called like that? Well, result register is when A to D0 DR0 صح? Low and high. A to D0 data register 0 مثلا. This is a 16-bit register. 16-bit. Bit 0, 1 up to 15 صح? We said our data can be 8-bit or in blue 10-bit. If it's 8-bit, the 16-bit register is this part is called ATD0 data register 0 low, and this is called A to D0 data register 0 high. Same for data register 1 and 2 and so on. طيب, the 8-bit, if they're right justified, مثلا I read what? 8-bit, I don't know, 1 0 1 0 1 0 1 0. They'll be stored like this here, right justified. 0 1 0 1. These are 4 bits. 0 1 0 1. This is called right justified. If you do left justification, justify, then these will be stored here. Yani 1 0 1 0 1 0 1 0. ماشي. It really doesn't matter in the case of 8-bit, but in the case of 10-bit, if you do right justification, 10-bit right justification, then your data, you have 2 extra bits, صح؟ يعني 0 1 0 1 0 1 0 1 0 1. Then this way, you will have to go and concatenate the results of the high part with the results of the low part, or just go take this whole thing, the 16-bit, read it once. If you're doing right justification. If you do left justification, it will store your data like this. And let me choose a different color, black maybe. ماشي? Your data will be 1 0 1 0, 1, 0, 1, 0. These are 8. And then we have 2 more, 1, 0. You can still concatenate, right? You can still go get this and get this one. But in this case, you need to get rid of these lower 6 bits. What does it, either you shift the numbers 6 bits to the right and you get your number. But usually we use this left justification if these 2 bits don't matter. You don't care about what do these 2 bits represent. We said if we're doing 10-bit A to D, then we're representing the voltage from 0 to 5,000 millivolts using 10-bit, using numbers from 0 to 1023. So the step size would be 5,000 divided by 1023, or resolution if you want to call it. How much each number would represent in terms of voltage? It would be 4.88 millivolts, right? So the worst case scenario, you can take the most 8 significant bit and ignore the lower 2. The lower 2, if you assume they're zeros, or if they're ones, in worst case they're ones and you assume they're zeros, so you lost about 5 millivolts times 4 and 20 millivolts, which is not a big deal in some cases, and you choose to ignore them. You just consider them as zeros and you read the most 8 significant bit because they're of heavier weight. Is that clear, guys? Hope it is. Meshi, so you can set this bit to do right justification of the data or left justification of the data. So in our case, we're going to do 8 bits, so let that be on the right in the lower register. So right would be, this would be 1, so yeah. The data, if we want to read, do we want to be to have it in a signed or unsigned format? I'll give you what is the difference, but let's start with do unsigned 0. Well, let me show you real quick what does signed versus unsigned mean. If you pick to do signed numbers 8-bit, signed or unsigned, let's start with unsigned. Unsigned means 0 voltage will be presented in 8 zeros, 8-bit zeros. And the maximum voltage, this is the V reference low, and the maximum voltage, if it was 5 or 5.12 voltage reference high, will be the all ones, the 255, right? And this would be the 0. You start from 0. This is for unsigned numbers. If you pick to choose to use signed numbers, signed 8-bit codes, then you start in the middle. So the half of this range is at 2.56. And this would be your 0. Meshi, this would be your 0. Going up, you will go up to 128, so 127, up to 127 at the maximum voltage, or go -1, -2, so to minus 128 at 0 voltage. You have the 2 options. And this is the same in case of 10 bits. So in signed, it means that you go to the middle of the range of the voltage you're measuring between voltage reference high and low. That's your 0. Underneath it is negative. Above it is positive. Right. So let's use the non-signed 0. Enable continuous channel scan. Sometimes you in the conversion here, you pick to do 3 conversions, or 1 conversion, or 8 conversions, whatever. Do you want to do it only once? The 3 converters, read 1, 2, 3, then stop, or read 1, 2, 3, then repeat another 1, 2, 3, then 1, 2, 3. Keep doing that forever. This is the scan mode. For us, let's do it only once, single. Whenever I want to read, I tell it in my code read. Okay, so let the scan be 0. Scanning multi-channel over multi-channel or single channel. This means, I just explained it, if you choose to do three conversions across a single channel, it will read the voltage on that pin 3 times. But if you do multiple channel, it will go to that pin, read 1 time, the one after it, AN1, then AN2. Okay, it will do across multiple channels. Let's do over single channel, so this would be another 0. And here will be the channel that we want to read. Yani if we want to read AN0, this will be 0, 0, 0. We want to read analog channel 1, this will be 0, 0, 1, up to AN7, so analog pin 7, this would be 7, yani 1, 1, 1. Huh? Okay, so for us, when we write our code, we'll take this from the user, from the code, yani let's not set it. So A to D controls register 5 will be, right, 0x8, this is 8, 0, or, this is an or, channel number. So إذا قلت له 80 or 1, it will be 81. 80 or 7, it will be 87. Or 0, 88, 0, right? So this is the value of our control register. Not to forget to say that anytime you try to write to register 4, yani change resolution, change speed, whatever, this will abort the current conversion. It will stop the current conversion going on. If you're converting, you go change this register value, you write to it, you're going to stop any conversion going on. Same as conversion, same as writing to control register 5. Any write to this register, it will stop, abort any current ongoing conversion. طيب. Also, any write to this register will start conversion. Stop ongoing conversion, start a new conversion. So there is no specific bit to say start converting. The moment you write to this register, decide the bit, the channels, you will start converting and sampling the voltage on that channel. Okay, so to start our reading, we will need to write to register 5. Okay, these are the registers for the 3 bits. The 3 bits, zeros will be 0, 1 will be 1. This is the table. And this is left and right justification, signed or unsigned. طيب, the status register. We said.
سؤال بس ممكن.
Yes, Mustafa, go ahead.
هلا في ريجستر 5 بقدر اخذ اكثر من channel.
Yeah, you can do. يعني احنا what we're going to do, we're going to write a function, Mustafa.
Okay.
Called A to D read. We pass to it a function C, a number. If we write 0, we pass to 0, we're going to read from channel 0. If you pass 1, we read from channel 1.
يعني الفكره انه الريجستر هذا اللي هو ريجستر 5 او الكنترول 5
yeah.
ممكن يتغير، يعني مش ثابت. خلينا نحكي اللي هو
yeah, you can write it during your program. Yes.
ايوه.
Of course, you can write it anytime in the program.
Okay.
Yeah. It's not fixed يعني. Yeah. طيب. Now, when I write to register 5 and start converting. طيب, I need to wait for a while, صح? I need to wait for a while to finish the conversion. Okay. How do I know that the conversion is done? It's over and the data is ready to be read. There is a bit in the status register 0 here, this bit, that will rise when the conversion sequence is complete. So we will need to be monitoring this bit. It by default is 0. So when we write to control register 5 and say read, then we go check this. While this is still 0, we stay waiting for it. While 0, we stay waiting for it. When it's 1, then the data is ready. We go read the data. طيب. ماشي. These things, these are the external trigger overrun flag, Fifo overrun flag. You know, Fifo, if you go right over a register that you didn't read yet, it will give you a flag. External trigger over, and you got external trigger to start converting, and then you get another trigger before done with the previous converting. So you get a flag to alert you about this. طيب. In the non-FIFO mode, guys, we said that A to D0, A and 0, sorry, A and 0 will store in result register 0, right? A and 1 will store in data register 1, صح? اللي هو, which way he said here. 0 will store in 0, 1 store in 1. This is in the non-FIFO mode. In the FIFO mode, where do you know, where is your result going to be stored? You don't know, okay? You don't know. You need to go check it. And these 3 bits will tell you where your result was stored in the FIFO mode. ماشي. طيب, for us, we pick the non-FIFO, so it doesn't matter. So what we care about this register is to keep checking for this check for conversion, done or not. Test register 1, this is only 1 bit that we can use, and we call a special channel conversion. If you want, sometimes you want to know what is if your battery powered, what is the value of your voltage source? What is your voltage reference high? What is your voltage reference low? What is the average of your voltage references? You can go make this bit 1 and go set these 3 bits here, or the channel, sorry, in control register, the channel in the control register 5 here, these ones. If you set them to 100, then you will be reading the voltage on the reference high. 101 voltage reference low. 110 will be the sum over 2, يعني their average. ماشي. Special, يعني it will internally go connect your channel to the voltage source or to the ground or whatever. This would be handy and useful if you want to monitor your battery power, if you're battery powered. Special channel. Status register 1. Okay. Remember when we talked about automatic flag clear, fast flag clear? This is it. These are the flags. Whenever a conversion is complete, yani, you said go do 8 conversions, store in 8 registers, or three conversions. When the first conversion is done, 8 conversions are these ones. I told them to go do مثلا 5 conversions. 5 conversions. How do you know that you're done? When this one is a 1, we're done with the first conversion. When this one is done, you're second, third, fourth, until 8th. Okay, so you need to check for these flags. But if we're using one single conversion, checking this would do it, or even checking this, where is it? The conversion sequence complete. This would do it. But this represents the whole sequence. This would not help you if you're doing 8 conversions. If you're doing 8 conversions, this would rise only after after you're done, after all of these become ones. طيب. ماشي. These will rise. How to clear them? If the automatic fast flag clear is 0 in the control register 5, then you will have to go read stat 1, this one. You have to go read this register. I mean, stat stat1, you will have to read this. Then you go read the data. You have to read this. And you say, if this, read it, bit ended with whatever equals 1, and then you read it. Then go return the value in A2D0 data register 1 or 2. This flag will be cleared. But if you choose to do the fast flag clear in the control register 5, maybe then you just go read the data register. This flag will clear automatically. And when would you want to do this? Well, when you have a single conversion. Why do I need to know that the conversion is done from here? Then I go read it, this one again. خلاص, I know it's done. I can go read the data, and this will clear automatically. طيب. This is about the digital mode. This is about the digital mode. I'll come back to it after an example. The clock conversion. Well, what should I do? Conversion, FIFO, I explained FIFO, these are examples. طيب, you know what, let's طيب. We said that we have these AN0, AN1 bits, the 8 channels here. These channels, this channel is by default, it's analog, but you can configure it as a digital pin where you can read it just like مثلا port B0, bit 0 or bit 1, as a digital port. So you will need to enable the bit to be digital. And when it's enabled, you'll find the data in the data register. Okay. That is, in this case, we call this port AD, digital port. زي ما كان, as we had port B, port H, port M, port A, we have port AD. In this case, it's digital, but you have to enable it to become digital. How do we enable it? It is through this register. We have a register called this one, A to D0, A to D0, digital enable. So if I want the first channel to be digital, I go write a 1 here. I want all the bits to be 1, I write 1, 1, 1, 1, 1, 1 here. Then they're digital. Okay. So you apply voltage push buttons, whatever, to those pins. Where is the 1 or 0 going to be? The data. You'll find it and register the data register, port AD0 for the first 7 bits, or port AD1 for the next 7 bits. This will be the data register, something like port H or port B. You just deal with it. This is the digital register. But first, you need to enable it to work in the digital mode. If you want it to work in the digital mode. طيب, we're here to use it in the analog mode. We already have enough digital ports. And we said that, yes, we can use the 16-bit register in high or low. طيب. The clock speed. And we computed the clock speed, صح? I'll come back to these things. Why do I choose 2, 4, how much time? I'll come back to it. Let's go do our example. We don't need this for programming purposes right now. We picked to do 2 stages in the sample. The first stage is 2 sample clocks. The second stage is 2 sample clocks. طيب. And we configured our clock frequency at 2 megahertz. 2 megahertz, right? So 1 over 2 megahertz is 0.5 microseconds. You know what? Let's get it done. 0.5 microseconds times. If you're using 8-bit resolution, our conversion time is going to take 8-bit resolution, and 8 plus how many samples for stage 2 did we choose? 2 plus 2, اللي هم stage 1. So the result is 12 times 0.5 microseconds, which is what? 6 microseconds. طيب, if we choose 10-bit resolution, we're adding 2.5, يعني 7 microseconds. Remember this? Remember this last time when we talked about conversion speed? It was somewhere here, 6 or 7 microseconds.
Yes, Doctor, 5 or 6 microseconds.
Here, 6 if it is 8-bit.
Or 6, 7.
Or 7 if it's 10-bit. This is the maximum speed. So this is how it was computed. Assuming that the second stage of the sample and hold is only 2 clock cycles. If you increase this, you'll increase. Meshi. If you make it 4, you're adding 1 microsecond extra. This is at 2 megahertz. You can slow down if you want. And this is a table that summarizes these. Anyway. Okay. Let's go do an example, guys. You're probably, we're ready to do an example. Well, I have wrote something. Do you want me to use it or write together from scratch? I don't mind though. Any is this time. I'm worried about time. So this would be class demo 10, huh? I write in the e-learning, I write a detailed explanation for each demo, what we did in it, right? You're aware of that?
Yes.
Yeah. Class demo 10. You know what? We still have 6-7 minutes. Let me go copy the code I wrote, and we go through it together. But not to, oh yeah, I just remembered. Let me show you, and I'm not gonna go bring analog voltage or connect. I'll show you some stuff. What is this? Let me stop sharing. See my phone camera? Remember when we did this potentiometer with the Arduino and we started changing voltage, right? I'm gonna do the same here on our microcontroller, this controller, but I'm not gonna go connect these wires and put this. I have a built-in potentiometer, same thing. This is it. Meshi. I'm gonna use it. We also have a light sensor over here, if you see it. See my screwdriver, a light sensor. I'm gonna use it. We also have a temperature sensor. And each of them is connected to an analog. The temperature would be somewhere around here. Meshi. So this is from the Dragon 12 data sheet. I pasted here. These are the built-in sensors. We have a light sensor connected to port AD4, analog port 4. We have a temperature sensor connected to analog port 5. We have a potentiometer connected to analog port 7. The right straightforward. Let's do this. Let's read the potentiometer, convert it to a voltage number from 0 to 5. display the voltage on our 7-segment display. Yani just like we're doing a voltmeter, Meshi, and we can get a voltage from anywhere, from a battery, from another external potentiometer, from any source, from a sensor. طيب, display it on the 7-segment display as a number from 0 to 5. Later on, when we take serial communication, we can send it serially maybe to the computer or to MATLAB. And let's read the light sensor and see if it's dark, we turn on LEDs, the red, green, blue LEDs. If it's bright, we turn off the LEDs. طيب. And we have a temperature sensor to read the temperature. And the temperature sensor connected to the board is the LM45. And I have put the data sheet for it under resources, and it's straightforward. I'm just gonna try to save time. The LM45 data sheet for this temperature sensor, it is built in on our controller. It's on our board. Sorry, this is it. It has a voltage source and ground already connected for us, and you get this voltage. You want to read this voltage. When you read the voltage using the A to D normally, when you read this voltage, how do you know the temperature? There's a formula, linear. Hey, the voltage you read is 10 millivolts per Celsius times the temperature. So this is something you know. You read it, right? So if I read the 255, what is the voltage? 5 volts, صح? If my voltage source is 5, then this is 5. I know this. This is known. And this is a 10 known. So the temperature outside is what? 5 volts divided by 10 millivolts. صح? Okay? So it's straightforward. Other temperature sensors have different formulas. But what you need to know the temperature, this unknown, is to know the voltage. How do I know the voltage? I just read it through the A to D. Okay, so let's go learn how to read voltage. Let's go learn how to read voltage. Meshi? So I'm gonna read in this sensor, in this example, the light sensor connected to channel 4, and the potentiometer connected to channel 7. And let me go to let me go to Code Warrior, and this is the empty. I'm gonna go copy my code that I have already and go through it with you. Copy, come here, Control A, Control V. This is some code I already have written before. First, the PLL function, we wrote it together, right? To raise the frequency, the clock, operating frequency to 48 megahertz. I have my delay function. We wrote it together. Now today we're gonna write these two functions. هذول مهمين. A to D0 init, initialize the analog to digital converter, and A to D read. Okay, and this is, we return 8-bit because we're gonna read 8-bit, and we provide it with an 8-bit number, which is the channel we want to read from. So this is the new thing here. These are the new things here. Initialize the analog digital converter, اللي هم what? A to D0 control register 2, 3, and 4. Then in the read, we write to control register 5 and wait for the flag to tell us that the conversion is done, and return the data register value. Meshi? So this is what we're going to do. Let's go, and this is the 7-segment display for the displaying thing. This is the reading, converting it to voltage. I'll come to this later. PLL init, A to D0 init. Let's go to our functions. PLL init, we wrote it in the past. The delay function, we wrote it in the past. You can replace it with the delay function we use with the interrupt, up to you. But this is the new thing here. ماشي؟ طيب, A to D0, we wrote this together, صح? We said we're going to write init initialize it يعني power it up and do fast flag clear. So C0 from the slides, remember? Should I keep switching here?
Yes دكتور شكرا.
خلاص, we wrote it together. والله I erased it, sorry. But if you go now here, this is it, right? 1 1 and everything is 0. This is C0, I wrote it down. So ATD control 0, C0, power up. Now, after powering up, usually even the microcontroller, when you power it up, you need to wait a little. You need to do a reset so the circuits will stabilize. Okay, so it is recommended that you do some delay after you power up. So I called my delay function here. Then we wrote this as a 08. We did it together in the slides. We picked single conversion in the non-FIFO mode. Then here we picked 8-bit convergence, the resolution, 2 clocks for stage 2 of the sample and hold to work at 2 megahertz. And our PLL E clock is 24 megahertz. We did the math, it was 85. يعني Mustafa told me 85, صح?
صحيح دكتور.
If it's wrong, اكتبوا مصطفى. طيب. So this is to initialize everything. We set the resolution, we set the speed, and we powered up. Now the read, I want to start reading. I'm gonna pass the channel number as an 8-bit number from 0 to 7 and return the data after done with the successive approximation. So how do we start converting? We write to ATD control 5. So ATD control 5 equals 8 or channel number that we passed. This is what I wrote. طيب. Then you start waiting for the status register bit 7. يعني while ATD 0 status register 0 ended with 80, you mask all other bits except the most significant bit, right? While it is 0, it's going to be false, right? But I want to get stuck here. I want to stay stuck here while it's 0, so I put a not here. So stay stuck here as long as this bit, which bit? This bit. As long as this bit is a 0. This bit is a 0, yani conversion is not complete. When it becomes a 1, then the conversion is complete and the data is ready in the data register. So I stay stuck here as long as this bit is 0. When it becomes a 1, the condition becomes false, right? 1 and 1 become a 1. 1 not 1, yani 0, while 0 is false. So you move to the next statement, which is the return. What do I return? The data result, data register 0, low, the lower 8-bit. Meshi, I returned it. Right. This is the function. Now let's go to the program. The program, I have a 7-segment display. I defined 2 unsigned characters, one called my reading and one called my voltage. My reading is going to be the number, the 8-bit number that I'm going to read from the A to D, the number from 0 to 255, the digital number. طيب. So in the infinite loop, طبعا we called the initialization for PLL, the initialization for A to D. We configured port H as output, port P that has the red, green, blue LEDs. I'm going to use them as output. Then in the infinite loop, what do we do? I say A to D 0 read channel 7. Channel 7 connects the potentiometer to it. Meshi? So read it. It's going to return an 8-bit. I am going to store it in my reading. So my reading is going to be a number between 0 to 255. طيب, if we configured the A to D to 10-bit, the number is going to be from 0 to 1023. In this case, my reading cannot be a character. It has to be an integer, because it's more than 8-bit. طيب. And we said this number we're going to need, we're going to convert it to voltage from 0 to 5 and display it on the 7-segment display. So what did I do? I'm going to take the number, my reading. How do I convert a number from 255 to 0 to 5? Yani I have a number from 0 to 255. This is my reading. it corresponds to voltage from 0 to 5. How do I convert this reading?
5 على عدد السامبلز.
The voltage equals what? What I read.
الرينج
reading what I read. It's only an 8-bit reading over
by 255
times
5
by 5. So if I want to convert it to 4 digits, يعني 5,000 millivolt, I multiply it by 5,000, right? Right? Depending on how, but I only have one 7-segment display. If I have two, I can do 5.1, 5.2. If I have 4 7-segment displays, I'll do 4 digits. But now I want to do 1 digit, 0, 1, 5. Yani anything between 0.1 volt will be what? A 0. I didn't reach the 1 volt yet, and so on. طيب. So this is how we do it. طيب. Guys, ركزوا معي. If I do voltage equals my reading divided by 255 times 5, is this correct? Yes, right?
But maybe the output will be decimal or...
Yes, thank you.
Points,
Thank you, Talal. So if you do this in your code, you will find that your reading always either as a 0 or a 5. Why? Because your reading here is always a number between 0 to 255, right? Yani anything from 0 to 254 divided by 255 is going to be a fraction, point something. And we're using integer math. This will be converted into a 0 times 5 is 0. This is going to be always 0. طيب. So when it becomes a 255 divided by 255 is 1. 1 times 5 is 5. So you have always, your reading is always 0 or 5. So to overcome this data manipulation, what can we do? We can write the same thing. Multiply the reading by 5, then afterwards divide by the 255. Mathematically is the same, right? But in terms of integer math, this is better, right? Because you're reading times 5, right? So, مثلا, your reading is 1. 1 times 5 is 5 over 255 is going to be 0. Until you get what? You exceed the 1, the 1 volt. اللي هي going to be 19.5 millivolts time 1000 divided by 19 millivolt. This is a number times 5. You start exceeding. This is going to be a number more than 255. So you'll be a 1 point something. The point something will be lost. You keep the 1, and so on. So this will give you the whole range 1, 2, 3, up to 5 volts. But you're going to lose the fraction. Well, to get a better resolution, you can multiply by 50. You get a 1.1 volt, 1.2 volt, whatever. If you multiply by 5,000, even much better. You get in the things in terms of millivolts. That's why I wrote this here in this way. So if you write it, whoever has to leave to his other class, you can watch the recording. I'm gonna just do the demos and here. So my voltage, if you write it like this, if you divide by 255, then you multiply by 5. Sorry, where is the multiply by 5? Mathematically is still math is correct, but integer math will result in zeros all the time except when the reading is 255. Meshi. Okay, then my voltage. So I have a number from 0 to 5. This represents my voltage. I want to display it on the 7-segment display. I pass it through the 7-segment map. Invert it because I have a common cathode, common anode instead of common cathode. Then I want to read another. Who asked me this? Mustafa or Yazid? I want to read the light sensor. See, I can call the same function again, A to D read, but this time I'm going to pass the 4 here instead of the 7. Here I read the voltage on the potentiometer connected to the pin 7. Now I want to read the voltage connected to pin 4, which comes from the light sensor. I want to check it if it's less than, the reading here I'm going to read is a number between 0 to 255, right? You can go calibrate it, you can find the sensor data sheet, but this is very rough I'm doing here. If it's less than 127, yani less means darker, okay? More means brighter. So if it's less in the middle, less than 127, I want, less means darker, yes. And in that case, I want to turn on the light. So I go right once to port P bits 5, 6, and 7, right? Which are 4, 5, and 6, which are the red, green, blue LEDs. Else, I turn off the LEDs. Yani it's already bright. Turn off the LEDs. Tamam? This is the whole program. So I'm reading 2 different voltages on 2 different channels using the same function. طيب, let me program it. طيب, full chip serial monitor program column 3. Okay, done programmed. Let me turn it into the this mode. Let me stop sharing and share my other camera and pin this camera. You see this, huh? So I just programmed this. I just programmed the controller. I'm going to reset it. First, the 7-segment display. See this potentiometer? I'm using the screwdriver to turn it on. This potentiometer is similar to this potentiometer that we use with the Arduino. I didn't want to reconnect something similar, but it's because it's here. So I'm going to turn on the LED, turn the screwdriver left. Oops, sorry. Now I'm to the maximum left, and the voltage is 0. Huh? I've started turning right. It is turning. It's still 0. It's not going to become a 1 before we exceed the fraction. Now it's 1. Increment. Keep turning right. 2 volts. 3 volts. Keep turning. 4 volts. Up to 5 volts. And if you look at my scope, let me turn it on. I connected the scope. I connected the scope to analog channel 7 here. Okay, this is my scope. Turning on. So the voltage here is 5. Huh? On the scope, it is 1 fraction per one scale per volt. And turning down. See it going down? Now we're at 0. And here we're at 0. Over there, it's at 0. I'm turning on. Now it's at 1 here. I'm increasing. It keeps increasing until we get to the 5. Okay? This is the first A to D. That is, we made a voltmeter here. Okay? And the second part is the light sensor. See, it's dark right now. So the light here on the red, green, and blue LEDs is is turned on. This is the red, green, blue. This is the light sensor. Now I'm gonna turn on my light. I cannot turn on my lights. Like, how do I turn on a light? Okay. How do I turn on a light? Where is some? Do I have a light here? Okay.
نفس من الكاميرا تقدر تعمل اون على طول كونه فيديو.
والله؟
يس الفلاش تاع الكاميرا.
يعني I'm going, it's not accepting, cannot turn on flash because the light is what? Light is being used by another app. See? طيب, let me show it to you this way. Let me turn off the camera. Turn on the flash. Turn on the camera. Turned off the flash والله يا guys. طيب, you know what I'm gonna do?
اعمل العكس، اعمل تيرن اوف لللايت عندك مثلا، او غطي على السنسور مثلا بشيء.
لا مو مغطى. It's dark بالنسبة له now. The threshold I have. I want to make. Wait me for a second, Wait me for a second. Okay, guys, I'm back. And here's my light, see it? I got a phone with a light. And see, I'm turning on the light. See, I'm bringing the light closer to the light sensor, and the 7-second display, the red, green, blue LED is turned off. I remove it, it turns on. Now it's light, it turns off. Dark, turns on. Okay? ماشي.
طبعا دكتور، بس بالنسبه للكونكشن او السيركت بس ماخذ من بورت لبورت وفي سي سي بس.
What circuit? What circuit?
هون على البورد.
Here?
Yes.
There is no circuit. أنا بس موصل the only thing I have here is the scope, just to monitor port 7.
بين البورتس يعني بين نحكي بين السنسورز
The sensor is connected directly, the voltage. Remember when we connected this potentiometer, voltage divider? Yes. I just took the voltage. يعني, you know what, Mustafa? If you guys have time, يعني, I can just go bring any voltage from the battery. Put it to port on analog pin 3. You find it here. And go right in our code, read AN3. You'll get the voltage over there from 0 to 5. Yani directly connect a voltage source from a sensor or from a battery or from wherever.
طب دكتور هون بالاكزامبل اللي احنا عاملينه.
Yes.
هلا من السنسور او من نحكي من الثير بوتنشيوميتر اللي على البورد هي باي ديفولت موصله يعني.
It is connected. Yes, let me show you the schematic. You want
يعني ما في مثلا واير من
لا internally يا مصطفى.
internally. اوكي.
كله internally.
لا, it is connected on the board. See, يعني you see my mouse.
مش في screen.
This is the sensor, Mustafa. See, this is the light sensor. Internally, it is connected to the pin.
مش عامل شير دكتور.
لا تعمل شير سكرين.
Sorry. Okay, let me share in a second. Where is my share? This is the board, Mustafa.
Okay, doctor. Yes.
Okay. This is the light sensor I just showed you. This is it.
صحيح.
This is the red, green, blue. When I turned on a light here, this turned off. Now this is an LDR. It could be an LDR resistor in a circuit, okay, where you get direct voltage from the circuit connected to the analog port 4. This potentiometer, you know how it's connected? It's connected like this. The potentiometer is a variable resistor, right? You connect it to a voltage source and ground, and it has 3 pins, صح? This is the first pin, and this is the ground, and the third pin is the voltage out. And this is taken to the HCS12 ATD connected directly. So we're reading voltage here. The voltage divider is already built for us. When I use the external potentiometer, when I use the external potentiometer, how do I spot? Maybe you didn't forget, مش مقبول, صح? Spotlight. So when I did this potentiometer, remember when we did the 7-segment display, the Arduino model base? How do I connect it? This is it. I connected voltage source to this pin, ground to this pin, and took the middle pin to the analog voltage, to the analog. So I built my circuit here, Meshi, on the breadboard. For the Dragon, it is built for us. This is it. The LDR, same thing. The LDR is what is LDR? Light dependent resistor. LDR, light sensor, light sensor, Mustafa. Do you see me back? There is something called LDR. LDR, light dependent resistor. So it is the same thing. It's like a resistor, but you don't turn something to change the resistor value. You put the resistor in a circuit. You can put something here, voltage source, and put the LDR here, and take this to ground. Let's say, well, let's do it like this. This is the LDR, and this is your voltage source. This is your ground. This value of the resistance of this changes with the light, either increases or decreases. Let's assume it increases. So you can, if it increases, well, you will have to have another resistor here to protect, صح? And you can take this voltage from here. So here, when this is very low resistance, you're connected to 5 volts, right? When this increases with light, more resistor, the resistance here becomes higher, the voltage drops down. Okay.
دكتور مثل variable resistor.
عفوا؟
مثل variable resistor.
What is variable resistor?
هلا ممكن انها تكون مقاومة متغيرة حسب شو.
LDR, light sensors, light sensors are usually called LDRs. LDR are, yes, they are variable resistors. The resistance value varies depending on the light surrounding it. That's why they call it light dependent resistor. Okay. If we look at the schematic, maybe not this one, maybe this is not going to help us. If you look at the schematic, where's the schematic? Where is the schematic? Maybe it's compressed. It's compressed. I have it here. I have it here uncompressed. I have it here uncompressed. So if we go to the schematic, it should be in one of these. And here we want to rotate clockwise a few times. طيب, do you see the LDR? What is this one? Here are the analog ports. See? This is AN7. Mustafa, are you still here? You want? This is the potentiometer. See? Just like when we connected it.
Yes,
connected to analog 7.
Yes.
Now, analog 4, where is analog 4? Not, it's here. Hiya, horn, but maybe the details are in another and 10. It's again, Mustafa, it's another voltage divider. Yani anything you get from any sensor should be voltage. Okay? To be able to read it using the A to D. Okay. Who has a fast way to rotate counterclockwise? طيب, and we need to find it. Where is it? Somewhere. It would show it. Can high, can low. Where is this? Should be somewhere. Voltage divider. Just put the LDR resistor, the light dependent resistor, which is the light sensor, and a voltage divider, and take the voltage to your pin. You can search for it in the schematic. Okay, guys. I think let me just, if you have to leave, it's okay. But let's finish this. To start tomorrow, we'll start serial communication. So we're done with this. The A to D we read, we did everything. We know how to do digital now. We computed the time. We know how much time it takes. These are examples of the Fifo mode or non-Fifo mode. So the example over here says, if you're gonna start reading from channel, you're gonna do 5 conversions and start storing at data register 5, start reading from channel 6 for 5 conversions. In the Fifo mode, you're gonna read channel 6, 7, then 0, 1, 2. These are the 5 conversions starting from channel 6. These will be stored at result register 5, 6, 7, then wrap around back to 0, 1. This is in the Fifo mode. In the non-Fifo mode, A and 6 will be stored in register 0. 7 will be register 1. Always, you start from 0 and save according to the number of conversions you're doing. You're doing 5 conversions, you store from 0 to 4. You're doing 6 conversions, you store from 0 to 6. If you're using the Fifo mode, you start from the location specified in the stat register 0. Okay, this any more examples on what is Fifo, non-Fifo. And this is how the procedure to program the A to D converter. We already did this right now, practically. Some code, we already did it. We're done with A to D, okay? Next time, we're gonna start with serial communication. Thank you for your time. I'm gonna stop sharing and you may stay for questions if you need. See you tomorrow at 5 p.m.